Hello, my name is Scott Bryson, and I am an applications engineer for Texas Instruments' current and position sensing product line. In this video, we will discuss how linear Hall effect sensors may be used to measure absolute angle position. Many applications rely on sensed position feedback to determine the state of the system. When the object is rotating, there are cases where incremental encoding does not provide enough resolution, or might not be able to detect the initial conditions at power on. Having the ability to define the absolute angle of the target, even at power up, provides more robust operation and greater utility in design. A few examples where angle sensing is important to overall system function are industrial robotics, electronic steering mechanisms, and various consumer goods, which feature dial interfaces, such as digital thermostats. A rotating diametric magnet is most commonly used with Hall effect sensors for this purpose. If we consider a top-down view of the field vectors produced by this type of magnet, we can observe curvature of the field around the magnet. With any Hall element, only the component of the vector which is orthogonal to the sensing element will be sensed. When we place a sensor facing the pole of our magnet, we can trace out a path around the magnet and examine the field vectors as if the magnet were rotating. We notice, as the sensor is exposed to the magnet at various angles, that the resulting plot of field strength versus angle appears to be sinusoidal. With a single sensing element, we can use this behavior to perform a rough angle calculation. When we know the amplitude of the expected magnetic field, we can estimate the angle based on the expectation that the output is equal to the sine function with an amplitude represented here by alpha. For example, when we look at the plot representative of actual components from a real magnet, we might consider the y component. At 90 degrees, we observe that the field has a magnitude of negative 25 millitesla. We might be interested in determining the angle when the field is about negative 20 millitesla. We can solve for theta and find that this will occur at about 127 degrees. Using this method, we should be able to monitor up to 180 degrees of rotation. However, if the magnet were ever allowed to travel more than 180 degrees, we could not determine if the magnet were at 53 or 127 degrees rotation. This limited visibility can be problematic for many rotating systems. To expand the view to a full 360 degrees, we need to add a second Hall effect sensor, which is 90 degrees out of phase. If we monitor the y component of the magnetic field with both devices, we will obtain inputs as shown here. This provides us with both a sine and cosine function, which we can use together. The arctangent function will now enable us to determine the rotation angle for all positions. In many math libraries, it is useful to consider the atan2 function, as this simplifies the calculation by accounting for the sine of b1 and b2 during the process. Implementing a two-sensor configuration is possible with a variety of configurations. One method is to use two distinct linear Hall effect sensors which are mechanically separated by 90 degrees. With this approach, there are two basic alignment options. The first arrangement uses surface mount devices placed beneath the outer face of the rotating magnet in an out-of-plane alignment. This is sometimes also referred to as off-axis. In this position, the sensors will be sensitive to the z component of the vector. A second option is to use through-hole devices which are placed coplanar or in plane with the magnet polarization. Sensors in this location will detect the field directed radially outward from the magnet. With the second sensor rotated 90 degrees about the center of the magnet from the first, each sensor will be exposed to the same field over one full rotation with a 90-degree phase difference. This is a simple way to set up the required signals for angle calculations. This configuration does have a few drawbacks, which include that the application may have limited physical space available for the exact placement of two sensors. There may be sensor alignment errors that occur during assembly, and sensitivity errors that result from device-to-device variations must be accounted for. To help reduce physical space requirements and ensure 90-degree phase alignment, Three-dimensional position sensors integrate mutually orthogonal sensing elements for each direction in a single package. This allows the device to provide a more complete view of the magnetic field. A device that has sensing elements capable of detecting multiple components of the magnetic field provides much more mechanical flexibility than a one-dimensional sensor. If we revisit the plot from the real magnet shown before, we could now select the Z and Y components for this calculation. These two components are inherently 90 degrees out of phase throughout the entire magnet rotation. We now do not need to worry about alignment from channel to channel, and each Hall element in the same package will typically demonstrate better overall sensitivity matching than would be expected from two discrete sensors. Again, we have a number of alignment options for 3D position sensors. The sensor will observe ideal fields for this application when placed along the axis of rotation, or on axis. The device might also be placed in plane, as we saw before with the one-dimensional sensor, or just about anywhere out of plane where there is sufficient magnetic flux density. In every case, there are always at least two components available to perform arctangent calculations. Revisiting the real magnetic field components one more time, it is noteworthy that the component magnitudes are unequal. In some applications, it may be possible to place the device in an ideal location or rotate the device in place to help average two field components, but in many cases, this amplitude mismatch will be unavoidable. Even if the magnetic field inputs to the device are perfectly matched, there is still sensitivity mismatch, which can result with a small inequality between the two channels. Depending on the magnitude of the difference, this error can become quite significant. Here, our peak amplitude difference of about 4 millitesla between BY and BZ results with a worst-case angle error of over 4 degrees. In order to achieve the highest angle precision, it is necessary to normalize the two vectors to each other. This may be done by applying an attenuation factor to the larger of the two signals, which is BZ in this case, in order to reduce it to match the other component. In our example, BZ measures about 29 millitesla, while BY measures 25 millitesla. If we scale down BZ by 86%, we will expect less than 0.5% of mismatch between the two signals, and the resulting angle error from these sources will become virtually non-existent. This function is built into devices such as TMAG 5170 to help quickly enable this measurement for all alignment options. The total error in any system will also depend on a number of other factors such as noise, rotation speed, and magnet rotation errors like tilt and wobble. Reducing the impact of these errors is possible, and more details regarding these solutions and how to design for precision measurements is discussed in our application notes. Linear Hall effect sensor angle measurement theory, implementation and calibration, and angle measurement with multi-axis linear Hall effect sensors. In these documents, more detailed discussions on angular position sensing are outlined, along with real examples that implement full 360-degree rotational sensing and their calibrations. If you would like to learn more about Hall effect sensor portfolio, please visit ti.com/Hall effect to explore our technical resources and products.